Welcome to the next class of coordination chemistry. Today we are going to study about stability of coordination complexes. Most of the coordination complexes are highly stable, but in aqueous solution they undergo slight dissociation and attains an equilibrium with the central metal ion. So, before studying the stability of complex, we can study about some terms in related to stability, and the first one is equilibrium constant. You know what equilibrium constant is. To find the equilibrium constant, let us consider a reaction. 2a plus 5b gives 3c plus 4d, and a and b are the reactants and c and d are the products. So the equilibrium constant k is the equilibrium constant, and the equilibrium constant is the concentration product of the concentration of the products divided by the product of the concentration of the reactants, that is K equal to products divided by reactants. So we can write that equilibrium constant K equal to C, concentration of C raised to 3, since there are 3 moles of C, so we write concentration of C raised to 3 and concentration of D raised to 4 divided by concentration of A raised to 2 and concentration of B raised to 5, and this K is called the equilibrium constant. And if K is large, then products are favored. That means a forward reaction will take place if K is large. That is the equilibrium constant. Let us consider another reaction, that is NH4OH dissociates to NH4 plus and OH minus. So this is a dissociation step. This ammonium hydroxide is dissociated into ammonia and OH minus, NH4 plus and OH minus. So we can write the equilibrium constant like this, that is K equal to NH concentration of NH4 plus, that is product, into concentration of OH minus divided by concentration of NH4OH. So since this reaction is a dissociation reaction, we can say that this is a dissociation constant. Instead of equilibrium constant, we can say this is a dissociation constant. So dissociation constant is NH4, product of NH concentration of NH4 plus into concentration of OH minus divided by concentration of NH4OH. That is equilibrium constant, and in this reaction, that is dissociation constant. And if the reaction, if we consider this backward reaction, there's a formation, this NH4, the combination of NH4 plus and OH minus gives NH4OH. That means this step is a formation step. So in this step, instead of dissociation constant, we can say that is a formation constant. So equilibrium constant, in some cases it will be dissociation constant, and in some cases it will be formation constant. And coming to the stability of our coordination complexes, there is some generalization, that is smaller the value of dissociation constant, greater the stability of the complex. So again, I am repeating, the smaller the value of dissociation constant. If dissociation constant, that value is smaller, the greater will be the stability. That means that reactant will be more stable if the value of dissociation constant is small. In other words, we can say that the reciprocal of dissociation constant is called stability constant. So that means if the value of stability constant is greater, what will happen? Reaction stability of that complex will be greater. That means no reaction will take place. Reaction will take place only slowly. So if the stability constant, the value of the stability constant is greater, that complex will be more greater. So the stability constant and the dissociation constant are just inverse. So the value of dissociation constant is smaller, then greater the stability of the complex. In other words, if the stability constant is greater, then the complex will be greater. That is stability of coordination complexes. And here we can see some reactions. This is a stepwise formation constant or stability constant. That is the formation of a complex in solution proceeds by stepwise addition of ligands. Here M is the metal and L is the first ligand. So M and L combines to give Ml. So we can say the dissociation constant, that is what K1, that is not it's not dissociation constant, it's formation constant, since this reaction is a formation reaction. So K1 equal to concentration of Ml divided by concentration of M into L. And the next step, again this to this product Ml, again we are adding second ligand. So the product we get Ml2. So in this formation constant equal to Ml2 divided by Ml into L, the concentration of Ml2 divided by concentration of Ml into L, like that. If again we are adding one more ligand, we will get that Ml2 plus L gives Ml3, like that. Ml raised to minus 1 plus L gives MLN. So the reaction is Kn equal to MLN by MLN minus 1 into L. And this K1, K2, K3 and Kn are called stepwise formation constant or stepwise stability constant. So in this, these reactions will take place in a stepwise manner or stepwise addition of ligands. So we termed it as a stepwise formation constant or a stability constant. And next one is an overall formation or overall stability constant. Here, see this reaction, M plus L gives Ml. And the next reaction, again this metal is added to two ligands, M plus 2L, not like previous reaction. The previous reaction, this is in the second step, Ml plus L gives Ml2, but in this reaction, M plus 2L, again separate reaction, Ml2. So we can see the what stability constant, formation constant. Here, beta 1, the formation constant is Ml divided by concentration of M into L, and here B2 concentration of Ml2 by concentration of M into L raised to 2, etc. like that. So we get that beta raised to N, beta N, that is MLN, concentration of M into concentration of L raised to N. This is overall stability constant. This beta N, we can say that is an overall formation constant or overall stability constant. So when we multiply this K1, K2, K3, Kn, etc. And cancelling the same same digits, we will get that that beta n equal to MLN by M into L, like that. That is beta n equal to K1 into K2 into K3 into Kn. So from these, when we are multiplying this K1 into K2, K3, etc., that is values of K1, K2, K3, etc. from these steps, we will get this value MLN by M raised to M into L raised to N. So this overall stability constant beta n equal to K1 into K3 into K2 into K3 into Kn. That is what that is overall formation or stability constant. And the next one is the factors affecting stability of the complex. And the first one is the nature of the central metal ion. These are the factors affecting stability of the complex. That first one is nature of the central metal ion. The stability of the complex increases with increase of charge density on central metal ion. So when the charge density on central metal ion increases, what happens? Stability of the complex increases. That is, greater the charge and smaller the size of the central metal ion. In other words, we can say larger charge to radius ratio. That means charge is greater and size is smaller. What will happen? Greater is the stability of the complex. So, in example, complexes of Fe3 plus is more stable than complexes of Fe2 plus, because Fe and Fe same thing, same central metal ion, same central metal ion itself, but 3 plus, the charge, that 3 plus is greater than 2 plus. So when the charge increases, what will happen? Stability also increases. In other words, when central metal ion, size of the central metal ion decreases, stability will increase. So for that, we can illustrate with an example. This is the first transition series: manganese, iron, cobalt, nickel, copper, zinc. These are the first transition series. So here, zinc has got the smaller size. So coming in the from left to right in the transition series, zinc is on the rightmost side. So zinc has got the smaller size. So zinc has got the greatest, zinc complex containing zinc has the greater stability. That is, the equation is like that: manganese is lesser than Fe is lesser than, like that. Zinc has got the greater stability. These are the first factor, the nature of the central metal ion, factors affecting the stability of the complex. And the next one is the nature of the ligand. Next factor that is affecting the stability of the complex is the nature of the ligand. So more the basic strength of the ligand, greater the ease with it can donate a lone pair of electrons. So basic strength means what? It can easily donate a lone pair of electrons. So basic strength increases, stability also increases. So we can consider some strong bases like Cn minus, F minus, ammonia, etc. etc. form stable coordination complexes because it can easily donate a lone pair of electrons. That is the nature of the ligand, second factor. And third factor is a chelate effect. So you studied about what chelate effect is. When if chelate ligands are present, there is an extra stability conferred to that complex, that is called chelate effect. So complexes containing chelate ligands exhibit more stability than similar unidentate ligand. It is illustrated by an example. Consider the stability constant of two complexes. That is a cadmium complex, two complexes of cadmium. In the first complex, that is cadmium and ethylene diamine. So it is a chelating ligand. So here the stability constant is 3.2 into 10 raised to minus 10. But the stability constant of a similar complex of cadmium, here it is another ligand, CH3NH2. So it is not a chelating ligand. So here the stability constant is lesser, that is 3.2 into only 10 raised to 6. This is the illustration that because because of the presence of chelating ligands, stability constant increases. These are the three factors affecting the stability of complexes.